Ever wondered how machines predict outcomes? Well, it's all thanks to a concept known as regression, a statistical approach that has a starring role in the world of machine learning. Regression analyses the relationship between a dependent variable and one or more independent variables. Imagine a puzzle where the pieces are variables. The dependent variable is the image we're trying to form, while the independent variables are the puzzle pieces. The goal of regression is to fit these pieces together in the most suitable way to form the complete image. This function, or fit, characterizes the connection between these variables. But why is this important? Because this function is the key to making predictions. It's like having a map that guides us to the treasure of accurate results and insightful conclusions. So, in essence, regression is a key player in making accurate predictions and drawing insightful conclusions. Now, you may be thinking, how does regression fit into machine learning? Well, regression is a supervised machine learning technique. In simpler words, it's like a mentor providing guidance to the machine to learn from data. It plays a pivotal role in predicting the value of the dependent variable for new, unseen data. Imagine a scenario where you want to predict the salary of an individual based on factors like years of experience, education level, or age. In this case, regression helps us draw a line of best fit through the data points to predict the salary for new data. Remember, regression works best with output variables that are real or continuous values like salary or weight. It's like a treasure map providing cues to estimate numerical values, making it an invaluable tool in the world of machine learning. So regression in machine learning is like the unseen force that helps us estimate or predict numerical values. To truly grasp the concept of regression, we need to understand some key terminologies. Firstly, we encounter the response variable. This is the primary factor we wish to predict or understand in regression. Also known as the dependent or target variable, it's the variable that we want to make predictions about based on the values of other variables. Next, we have the predictor variables. These are the factors that influence the response variable. Also known as independent variables, they're used to predict the values of the response variable. Now let's talk about outliers. These are observations with significantly low or high values compared to others. They can potentially impact results and are generally best to avoid in your analysis. Think of them as the odd ones out that don't play well with the rest of the data. Then we have multicollinearity, a term that sounds as complex as it is. It refers to a high correlation among independent variables. This can complicate the ranking of the most influential variables and can even distort your regression model. Finally, we come to underfitting and overfitting. Overfitting is when an algorithm performs well on the training data, but poorly when it comes to new, unseen data. It's like acing all the practice tests but flunking the final exam. Underfitting, on the other hand, is when the algorithm performs poorly on both the training and testing data. It's as if the model didn't study at all. These terminologies might seem overwhelming, but they're crucial in understanding and interpreting regression analysis. They help us comprehend the relationship between our variables and foresee potential issues that might arise in our analysis. Remember, the goal of regression is to create a model that accurately predicts the response variable based on the values of the predictor variables. These terms form the backbone of understanding and effectively utilizing regression in machine learning. Just like there are different tools for different tasks, there are different types of regression for different kinds of data relationships. Let's dive into the main types of regression: simple regression, multiple regression, and nonlinear regression. Each has its unique features, suiting different kinds of data relationships. First up, we have simple regression. This type is used when we want to predict a continuous dependent variable based on a single independent variable. The relationship between the two variables is assumed to be linear. So, if you have one independent variable to predict an outcome, simple regression is your go-to model. Next, we have multiple regression. This type is used when we want to predict a continuous dependent variable based on more than one independent variable, like its simpler cousin. Multiple regression also assumes a linear relationship between the variables. So if you have multiple independent variables, this is the type of regression you'll want to use. Finally, we have non-linear regression. As the name suggests, this type is used when The relationship between the dependent variable and the independent variables follows a nonlinear pattern. This provides greater flexibility in modeling a wide range of functional forms. When your data doesn't fit neatly in a straight line, nonlinear regression can be a powerful tool. Remember, the key to successful regression analysis is understanding your data and the relationships within it. Choosing the right type of regression is crucial in accurately modeling and predicting outcomes. In the world of machine learning, we have a variety of regression algorithms at our disposal. Each of these algorithms has its unique characteristics and applications, making them invaluable tools in the prediction game. First up, we have linear regression, perhaps the most well-known of the bunch. Linear regression assumes a linear relationship between our independent and dependent variables, meaning changes in our dependent variable are proportional to changes in our independent variables. It's simple, it's straightforward, and it's a great starting point for many machine learning projects. Next in line is polynomial regression. This algorithm takes our linear regression model and adds a little twist. By incorporating polynomial terms, it allows us to capture more complex, nonlinear relationships between variables. It's a bit more intricate than linear regression, but it's a powerful tool when dealing with more complex data sets. Last, but certainly not least, we have support vector regression, or SVR for short. Based on the support vector machine algorithm, SVR is a unique take on regression. It focuses not only on minimizing error, but also on ensuring that the errors stay within a certain threshold. This makes SVR a great choice when we need a balance between accuracy and robustness. These algorithms, while different in approach, all aim to accurately predict outcomes based on the data at hand.